In the last video, we explored how crystals are built by repeating a small building block, the unit cell, across space. Using cookie dough as our analogy, we saw how stamping the same shape over and over creates a perfectly ordered pattern. Now, before we uncover how nature decides its perfect crystal patterns, let's travel back to the 1800s and meet a remarkable mind, Auguste Bravais. Born in 1811 in France, Bravais was the kind of person who mapped snow-capped peaks by day and charted distant constellations by night. Using the math of geometry, he proved that nature follows strict rules. In 3 dimensions, there are exactly 14 unique ways to arrange a repeating lattice, and in a flat world, just 5. So today, whenever we talk about unit cells and crystal patterns, we're standing on the shoulders of a mountain-climbing, stargazing Frenchman who believed nature's beauty could be written in pure math. Before we think in layers and depth, let's begin on the surface, the simplest stage where atoms can perform their repeating dance. The question is, how many different ways can atoms repeat? Let's explore the 5 patterns. Start with a single point. We'll call this our origin. From the origin, we draw 2 vectors, a1 and a2. For simplicity, let's assume both are 1 unit long. Mathematically, every other point in the lattice must be reachable by sliding along combinations of those 2 vectors, where r is the resultant. Now let's mark a few coordinates. If we take n1 and n2 equals 1, and we know that our origin is 0, 0, we mark the points 1, 0 and 0, 1. We get the point 1, 1 as the resultant. Change n1 and n2 to 2, and the new point is 2, 2. The integers n1, n2 act like multipliers, helping us hop across the grid. By calculating and marking these positions, and then treating each new point as a fresh origin to apply the same rule, we construct the full lattice step by step. Not to forget, here, the angle is 90 degrees, and their lengths are equal. Together, they outline a square-shaped unit cell. In a similar way, we can start with an origin and define 2 vectors, even when they're not equal in length. And again, by plugging in different integer values for n1 and n2, we get new resultant positions. Each resultant becomes a new point in the pattern, and just like before, we repeat this across the grid to build the entire lattice. The angle between them remains 90 degrees, which gives us a rectangular unit cell. There's another variation of the rectangular lattice, known as the centered rectangular lattice. In this case, we still start with a rectangle. But what's different is that there's an extra lattice point right at the center of the rectangle. Instead of just having points at the 4 corners, we also place one at the center. This extra point changes the symmetry and repetition of the pattern, giving us a distinct 2D lattice type. And then, as usual, let's consider our origin. For simplicity, let's assume the lattice points are 2 units apart. We define our 2 vectors, a1 at 1, 1, and a2 at -1, 1. Using our basic rule, the resultant will be 0, 2. Let's go through the process again. We start with the origin as 1, 1, and define our vectors, a1 and a2 at points 0, 2, and 2, 2, respectively. As we calculate the resultant positions using the same formula, we now point out something we hadn't mentioned earlier. The angle between the 2 vectors is 120 degrees. This unique spacing gives rise to a hexagonal pattern, even though the process of generating the lattice remains exactly the same. What if something changes? Nothing is in symmetry. We still consider our origin and start with the process. The points might look like fractions. For now, let's consider random points 2, 0, 4a1 and 1.25, 2 as a2. We also get the resultant at 3.25, 2. How to calculate the angle mathematically? Theta is given by this formula. This gives us the angle theta between the 2 vectors, capturing the tilted, slanted geometry of the oblique lattice. In our example, it is 57.9 degrees. There's an other possibility. What if the angle is not acute, not 90 degrees? Even then, the same rules apply. Let's consider a set of vectors that form an obtuse angle. The coordinates might look a little trickier here due to the slant, but the process remains the same. We use the vector formula to get the resultant position. In this case, the angle between the vectors is approximately 97.1 degrees. Let's see what kind of shape is formed when we repeat this pattern. The unit cell takes the shape of a parallelogram since the vectors a1 and a2 are not equal in length, and the angle between them is not 90 degrees. Let's quickly summarize the 5 possible two-dimensional Bravais lattices based on side lengths and angles between the vectors. Number 1. Square lattice. Here, both vectors, a1 and a2, are equal in length. The angle between them is 90 degrees. So the repeating shape is a perfect square. Number 2. Rectangular lattice. In this case, a1 is not equal to a2. They have different lengths. But the angle between them is still 90 degrees. The repeating unit forms a rectangle. Number 3. Centered rectangular lattice. This one is a variation of the rectangle. Just like before, a1 is not equal to a2, and the angle is 90 degrees. But now, there's an extra point at the center of the rectangle, not just at the corners. Number 4. Hexagonal lattice. Here, a1 is equal to a2. Both sides are the same, but the angle between them is 120 degrees. This creates a honeycomb-like repeating pattern. Number 5. Oblique lattice. In this final case, a1 is not equal to a2, and the angle is not 90 degrees or 120. It's just some general value. It's the least symmetric of all 5. Imagine how a unit cell extends into 3 dimensions with 3 vectors. It looks like this. Earlier, we worked with just 2 vectors, a1 and a2, to define our 2D grid. But in 3D, we introduce a third vector, a3, pointing out of the plane. We now define 3 angles, alpha between a2 and a3, beta between a1 and a3, and gamma between a1 and a2. All crystal structures, no matter how complex, fall into just 7 crystal systems. While we have 4 main types of lattices: simple or primitive, base-centered, body-centered, and face-centered. Not every crystal system supports all 4. Each system only allows combinations that match its symmetry. And when we count all the valid combinations across these 7 systems, we end up with exactly 14 distinct Bravais lattices. Let's take a look at each of them. First, we have the cubic system, the most symmetric of all. All edges are equal, and all angles are 90 degrees. Think of a perfect cube, simple, balanced, and highly symmetric. Simple cubic, rare and fragile, but polonium takes this form. Body-centered cubic, for example iron in its alpha form, arranges atoms not just at the corners, but one right at the center. Face-centered cubic, copper has this structure. The structure illustrated here is only to understand the arrangement. Primitive tetragonal. Tin dioxide, also known as rutile tin oxide. This structure has atoms at each corner of the tetragonal unit cell, with no atoms inside or on faces. Body-centered tetragonal, beta tin. In this structure, atoms are at the corners and one in the center of the cell. This form of tin is stable at room temperature and is used in coatings. In the primitive monoclinic lattice, one of the angles, beta, leans slightly away from 90 degrees. Clinopyroxenes, formed in volcanic activity, crystallize in this way. Base-centered monoclinic adds an atom at the center of 2 opposite base faces. This slightly increases symmetry. Monoclinic sulfur, when cooled slowly from its molten state, can form this structure. Primitive orthorhombic. This is the basic form, with no extra atoms inside. Sulfur, in its crystalline form at room temperature. You might have noticed something interesting. Sulfur appears in more than one crystal system. Body-centered orthorhombic. This is like placing a single atom in the very heart of the box, giving the structure extra stability. Potassium nitrate, a familiar salt, crystallizes this way. Face-centered orthorhombic. The most tightly packed of the orthorhombic group. Barium fills every face center in addition to the corners, forming a more symmetric and dense pattern. Base-centered orthorhombic. In addition to the corners, uranium in alpha phase places atoms at the center of the top and bottom faces, boosting packing while still obeying symmetry. Triclinic. This is the most distorted of all crystal systems. Every edge and angle does its own thing. Kyanite, a mineral formed under high pressure, crystallizes this way. Trigonal. Imagine taking a cube and gently pushing it from one corner. You'd get a rhombohedron. Calcite, the mineral in limestone and chalk, forms this tilted yet balanced structure. Hexagonal. This system builds layers on a flat hexagonal base. Two sides are equal, and the angle between them is 120 degrees. Graphite forms strong sheets of carbon atoms stacked loosely. We started with 7 crystal systems and 4 lattice types, but only 14 combinations made the cut. Why? Maybe someday someone, maybe even you, will see patterns others missed. You could be the next to challenge these boundaries, or unlock a deeper reason why these rules are the way they are. Science grows when we ask, what if? So keep wondering, keep exploring. See you in the next video.